Welcome to the first lecture on thinking about data. This is actually the third time I've tried to record this. This is a new area to lecture on for me. I'm trying to do something unique here, and data in general is something you've heard about for a lot if you're now at the master's level. Congratulations, it's great. Data analytics and quantitative analysis and etc. It's many different synonymous or nearly synonymous words that go along there. I'm sure you're familiar with them. I'm trying to do something that'll maybe ground it a little bit to help you think about the why, so that whenever you encounter some of the whatever variety of technical permutation of data analytics or data analysis that you have to encounter in your day-to-day life, in your career, that you'll be able to approach it as beneficially as possible, even if the details of the specific technique are new to you. You can orient yourself as quickly as possible if you have a good philosophical base here. So I'm trying to build in this first lecture the philosophical base. I think that's the primary objective of this lecture. And I have a few other things that I think I would like to kind of work in there. So I want to start out with the idea that data analytics is this buzzword. And so as a buzzword, it gets full of it starts to undergo this semantic overload. Lots of people and entities, maybe not people individually, but groups of people working in concert, or maybe even just spontaneously organizing to this. They'll start to plug in different concepts they want to put in under the umbrella of whatever the hot term is now. And so this tends to happen when we have a term that becomes very popular, or its relevance to a large group of people it approaches or appears suddenly on the stage. And so there's a bit of semantic overload, at least in the education area, behind data analytics, or at least within the accounting education area. Everyone wants to be on the data analytics bandwagon, the data analysis, quantitative analysis, whatever you want to call it. We're just going to call it data analytics. That seems to be the most common way of phrasing this. Everyone wants to be on the data analytics bandwagon because it's getting a lot of attention. Everyone thinks it's really cool, and nobody knows what it is. Well, that's not really true, but in some way it is. In some ways, we don't have a common definition of what it is or why it's important. There are a lot of words. My current attempt at Chapter 11 says exactly that thing. I go through a paragraph. I'm going to rewrite Chapter 11, I believe. It goes through a paragraph of this description of what data analytics is, and my response to that is just so many words. Why can't you say it simply? It must be the only reason I would think that you wouldn't be able to say it simply and explain it clearly is that you don't quite understand. We don't quite understand. I won't put on the writer such directness. We as a group, or the general populace, don't quite understand what it is, or we don't want it to occupy its proper place in the lexicon as to what the term really means. Again, because we have all this semantic overload. Everyone wants to plug their pet project into data analytics, and everyone wants to say, well, it's what I'm already doing. Okay, so first of all, let's talk about what data is. Data is just information, and we are the humans that are trying to consume that information, and we're consuming it for a reason. We'll come back to that in a second, but we are humans. Let's stop with that. There's a lot of implications from that, and it will eventually be the foundation on which I'm building why we do so many of the things that we do. We're humans, and therefore we have actually a very narrow and focused ability to perceive. There are right now you can easily get up to a large number of things that you are ignoring in your immediate surroundings. I don't want to put a number on there, but maybe 100, maybe 1,000 if you really thought about it a lot, depending on how much you subdivide. There are things in your immediate environment right now that you are ignoring and not focusing any attention on. This is how we can drive on autopilot. This is how we can walk from place to place and not notice half the people there. This is how we get surprised by things so many times. It's because we just don't have the processing capacity to really. Our brains don't have the processing capacity to really engage the infinitely or nearly infinitely complex world around us. We think about your immediate physical surroundings, for example, the walls. When's the last time you thought about the walls or the ceiling or the floor or any of these things? As long as they're not doing something strange and out of the ordinary, something that calls your attention to it, you are happy that you get to ignore them. You don't want to think about them. That's a waste of your cognitive effort. Again, unless they're doing something very surprising. Oh, that wall is bending in a funny shape. Maybe that means something. Then you want to pay attention. Oh, look, there's water dripping from the ceiling. Maybe I should pay attention to it. Then, of course, you want to pay attention to it. But generally, it's going to stand on its own. Great. This is true in social situations as well. You get on the bus, you get on the train, you can sit in a classroom or whatever. As long as the people around you are not doing something out of the ordinary that draws your attention and says, hey, something is different here. That person, for positively or negatively, is somebody I need to pay attention to. Perhaps somebody walks in who's just super smart, or oh, wow, that person's really handsome or pretty or whatever, drawing your attention to that person. I know I get that a lot, but, also maybe this person's acting really strange. That person is muttering to himself in a strange way that suggests there might be some sort of something going on that I should pay attention to, or there could be something going on that I should pay attention to. As long as people aren't breaking the rules, you can go in and out of classrooms with hundreds of different people and notice maybe 2 or 3 of them. You really don't focus much attention on the many people around you or the many things around you because you can't. You don't have the processing capacity to do that. And so when we talk about data, here I have a set of data. It's meaningless. I literally did the random function and then pasted as values. But the idea is here we have this very simple data set, up to 30 different observations. They have a department number, so I'm identifying department number, and 5 data fields. And if you were to go through this list and we're trying to say something meaningful about this data, well, let's talk about that. Why do we look at data? Well, we're always looking at data. This is no surprise if you've followed along with how I justify cost accounting. We look at data, which is past information about the past, so we can make better decisions in the future. That is, I think, always, if not always, almost always, the reason why you look at past data. Perhaps there's some maybe I could carve out a little space for some sort of nostalgia. You look at previous information, perhaps to evoke a current emotional state. Perhaps you're looking through baby pictures or whatever that way. I don't know. Perhaps there's something like that. But I think even then you're trying to evoke a current emotional state so that you can be happier, and therefore you would be doing better things on into the future. I think that the future really is the focus of our cognitive focus. It's the meaning, the reason for why we look at data, why we look at anything, why we investigate anything. If you were to start looking, so I started the sentence and I stopped. If you were to start looking at this data set and just try to say something useful about it to help you predict something into the future, say, well, what kinds of departments tend to do something in data field 1 or something in data field 2 or something in data field 3 or 4 or 5, you'd be hard pressed. The working memory of the typical human, I believe, the average the psychologists have come to, a general consensus with some debate around the edges, is that about seven units of data, 7 different figures can be stored in your brain at a time. Let's extrapolate up to 10 maybe. Maybe we're above average. I don't know. Let's say about 10 things. Okay, great. You have here are your 7, and then you can have at the same time these 3 as well. Congratulations, you have 11. No, can't even have that. You have 10 data points out of a total of 210 in this very small data set here, and you're going to try and manipulate those within your limited band of focus, and to make some sense of them in the future. Now, it's very possible that those 10 units of data, those 10 cells that you have thought of, they are outliers, or they're just an anomaly, or they tell you nothing. They aren't big enough of a sample to tell you what you need to know. So once we get past just a handful of data, a handful of numbers to look at, we really pass the limit of our cognitive capacity to work on it in working memory, to work on it in the immediate term. And so we have to simplify the data set. So the vast majority of the things that we're doing are to take this unmanageable data. Our brains just cannot comprehend this field of numbers in front of us. We have to simplify it. We have to extract 1, 2, maybe 3 different numbers, and then we can work with those numbers. We have to also learn what those numbers mean and how they're constructed and what the limitations of that are, because there's a lot of bad data analysis out there. A lot of people take a number and they run with it, forgetting how the number was built, forgetting what the assumptions and limitations of that number are, what the possible alternative explanations for that number are, and it ends up with a lot of bad decision making when you do that. So my interest in this lecture is to talk about the data analytics side of it and the idea of simplifying data, and so that our brains can comprehend it. And I'm going to talk a little more about the psychology in a second. And then the next one I would like to talk about kind of, okay, let's try and think like a scientist. And I'm going to overlap somewhat with my Chapter 7 variance analysis lecture, but I think there's I just see a lot of bad reasoning with data out there. People, or at least I should say, I see it, including in myself, the human tendency to misunderstand what the data is actually saying and not put the proper caveats and limitations on what the data says. And so as a result of that, if you're half equipped with this ability to reason with data, you know how to use the tools, but you don't quite know the limits of that knowledge that you've derived from those tools, what the output of those tools say, you're likely to have some trouble as you try to do a good job for your company, do a good job in your own business, or whatever your role is in your career, or even in your personal life. You're going to see numbers and you're not going to quite be able to know what to make of them and therefore make better decisions in the future. All right, so back to perception for a second. There's the classic gorilla movie, A Gorilla Experiment, and I believe it's by Simons. So here it is, a selective attention test. And so yeah, right there on the clip YouTube shows us is the punchline. And so the video here is 1 minute and 22 seconds long with a period at the beginning which gives you instructions, and then it's actually shown twice. But the idea is you have these two teams, passing basketballs, and your task is to count how many times the white team or the black team passes the ball. I believe it's the white team so that you don't accidentally notice the gorilla. But the point is you have a focus. And again, our cognitive capacity is narrowly focused. We tend to, as long as we don't have alarm bells ringing that will tell us we should focus on something that we can ignore. We are happy as human beings to ignore them. And so yeah, you do this task. You say, how many times does the white team pass the ball? Your task is to count how many, and you're counting that. And the majority of people, when this test was first done, it's probably gone down because people see this. I've seen this video many times, and it's a staple of lectures about perception. They didn't notice the gorilla at all. So the gorilla walks into frame in the middle of this after the teams have been passing for a little while, and beats his chest there, and then walks off. And this is a person. Sorry, it's not. As you can tell, it's not an actual gorilla. It's a person in a gorilla suit. So why wouldn't people notice this thing which is so strange? Why? Because our focus is very, very narrow. We have to do that. You have around you one way to think about this actually is about I am going to a YouTuber to get his face on here. Yeah, so I'm going to come to that in just a second. You have this combinatorial explosion around you in life. I'm going to use the example of chess and simply say that actual life is infinitely more complex than chess. And I'm going to point that out and then talk about this thing I've noticed with this Agad Mator, his channel, which I've occasionally watched in the past. I'm not by any means a chess expert, but it's kind of fun to watch sometimes, at least to marvel at people who are chess experts, some chess videos. So life is infinitely more complex than chess. Chess has 16 pieces per player, 2 players. They're turn-based, so there's only one move each player can make in a turn. And each piece can only move, has significant limitations on where it can move. Besides the fact that your knight can only move a certain pattern, or your rook can only move a certain pattern, there also is this problem of you can't move through pieces. So okay, you've got significant limitations to how you can move on the board. And yet, one of the fascinating things about this guy's videos is how quickly, when he's narrating a game, he's going through some classic game between grandmasters or something, and how soon he says, okay, and now on move 12, on move 17, whatever it is, we've reached a position that has never been reached before. And I always almost do a double take when I say that. I'm like, wait, this is a board of 16 pieces total per person. Excuse me. So 32 pieces at 64 squares total on this board. Those are numbers that we can manage, right? But you're telling me that after just a few moves, we have now diverged, and there's never been a game that's been played, at least recorded on whatever database we're talking about. You must be using to make that statement. We have only after so few moves reached a game that has never happened before, and it's fascinating how quickly that happens. Because, yes, sure, chess is very simplified. Each piece can only move certain number of positions. There are a very limited number of pieces on the board, and you can only move one time per turn. But even with that, once those decisions start to stack on top of each other, the number of possible paths down the decision tree you can go just starts to explode exponentially. This exponential explosion of possible futures for a chess game, and then life is, your business life, your personal life, whatever it is infinitely more complex than that. Or yeah, I'll use infinitely. That's fine. So we have you have to simplify, or your brain would explode. You would literally spend all your time thinking about things and never come to a conclusion it's useful enough to improve decision making, and you would ultimately you'd starve to death because you would be thinking so long you wouldn't eat or drink. So we have to economize our thoughts. A way of symbolizing this is the idea of this chaos. You want the chaos to be manageable and ignorable, and you want to pull out the order from the chaos. You want to impose the order of the chaos. You want to pull out the order, pull out the information from this chaos. And so what I'm gonna kind of analogize here is the idea that each data set is a new country or a new room, someplace you've never been before. So if you've never been a place before, and especially if you have limited models for it, let's say this is your first time in a castle, so it's first time in a room of a castle, or it's your first time in a new country. I'll stick with the country. Room, country, you can think of a larger or smaller scale. It's your first time in a new country. It is chaos to you. Every single thing around you could be something you should be attending to for your safety and for your happiness. It is very possible that the person talking to you in some language you don't understand right now could be telling you, hey, would you like a ride in this taxi? Or, hey, give me all your money, I'm going to kill you. You don't know the language necessarily. Let's just say that you don't, for this new country example. You don't know the customs. You don't know if you're in a part of town that is known to be friendly or unfriendly. You don't know. All these things are variables, the chaos around you that you cannot manage. Similar to this data set. This is a very small data set here. Now, you need to bring order to it, and the way you do it is you do two things. One, you simplify it. You try to take the many pieces of data that you have and try to pull out some rules of thumb, some sliver of one thing that will summarize a whole column of data, or a whole row of data, or a whole table of data. You want one number, maybe a pair, maybe three numbers. You want just a few numbers, manageable set of numbers that can summarize some important information about a whole data set. And this is true about going to a new country. Those guidebooks that they try to summarize and they do their best, but the guidebook for a new country is ultimately going to give you just these little rules of thumb to try to get you, okay, well, let's get you through the door. Let's get you to survive going in this new country where you don't know the customs, you don't know the language, you don't know what natural dangers there are, you don't know if the snakes are poisonous, you don't know anything like that. Let's just get you some very basic rules of thumb. Let's teach you the word for bathroom. Let's teach you the very simple things you're going to need. So that's the first thing you do. And the second thing you do is you get comfortable with it. Eventually you learn the customs. Eventually you learn the language. And you no longer are working with your working memory, which is limited to 7, maybe 10 data units of data that it can juggle. But no, you have now learned, oh, you know what? Departments that are under 150 or so, I've learned in my long-term memory now that they tend to do this. And so what you do is you end up learning and moving over into long-term memory these routinized rules. And so then you can spend your time on what is an anomaly. Okay, so two things are happening. One, you simplify it, and second, you get comfortable with it. You learn the language. This new language, the chaos, the underlying the underlying reasoning and rationale behind the chaos starts to reveal itself. You start to learn, well, why would somebody be saying this? Why is this word or this sound following the other thing? Why is this particular piece of data the way it is, or what are some likely reasons? Okay, great. So we have lots of tools that are computational, quantitative tools that are designed to help us with this. This is our task with data. And most of the things that call themselves data analytics are those very tools. And if we understand this light, the idea of we're bringing order, we are piercing through the chaos of this data set because it's unknown. We're piercing through it so that we can actually, our brains can actually digest it. Then a simplified version of it, simplifications of it. Then we understand why we would want to do the data analysis. Well, because otherwise you can't use it to improve decisions because your brain can't handle the data. And two, it also can help you understand the natural limitations that are going to be there with these data analytics tools. They are, in the end, a simplification of the data set. They use assumptions about what they're saying, and you need to make sure you know what these things are saying. So, for example, I have here the sum, and then I divide that sum by the number of observations here. So there are 30, count 30 right here, different observations. You can also just look at the top number here. And so I divided the sum here by the number of observations, which gives us the average. Okay, so right here I have the average. So what does the average tell us? This is if you've never explained, you've never taught somebody the idea of average. If you're like me anyway, sometimes you might be surprised at how hard it is to explain what an average is satisfactorily or completely enough. So what does just a simple average tell us? It's one of our 3 or 4 different tools that tells us what's normal in this data set or in this set of data that we're talking about. This is just data field 1 within this data set. So it tells us what's normal in the sense that, look, if we took everybody, literally this is what happening mathematically. If we took all the data numbers, all the numbers in this data set in field 1 here, and lumped them together and then redistributed them evenly, each observation would have this number, 5,228. It doesn't say more or less than that. Now, this number is around 5,000 because I literally contrived this column by saying ran between 1 and 1,000 or 0 and 1,000, something like that. So it's going to gravitate, each of these is going to gravitate till right around 5,000. Yeah, because I did that for each of these. So the average of these is 5266. Okay, so yeah, the average of averages there. But the point is, this average tells us it's a question of redistribution. If you smooth all the observations out, smooth them all out in terms of redistributing their value, this is the number you would have. Now, there are serious limitations to that. What happens when observation 23 includes 900,000? Some strange outlier. Well, we have moved our average from 5,000 something to almost 35,000. It has shot the average way up. Does it really change anything for the other 29 observations? No, it hasn't. Okay, so we have limitations. If we don't think carefully about what an average is, we're going to take an average and say, oh, well, blah, whatever. It is what's normal. No, it's one way of describing what's normal, and it's susceptible to outliers. So the average can be dragged to one end of the spectrum by an outlier. Down here I have standard deviation. We'll talk about that in a bit. Another idea here is the idea of median. And so let's just go ahead and we're going to go to data field 3 here. We're going to sort from smallest to large. No. I'm going to put a break in there. Maybe that'll teach it. We're going to sort from smallest to largest. Okay, good. Okay, so now we have smallest to largest, and we have a total of 30. It's okay. Let's keep the observation number. That's fine. We have a total of 30 here. I'm going to want a separate one, though. I'm just going to call it count number. Okay, because I need to get to the middle number here. All right. So when we've rank ordered them now, we have them from smallest to largest, and now we have if we go to the middle, another way of looking at what's normal is, well, let's rank them. Let's rank them, and whatever is in the middle is what's normal. All right. Well, in the middle here is kind of between 15 and 16, and so I'm going to take the average of these two. So 5289.5. That's what's normal. That's the median. So a median is another way of describing what's normal, and it has the benefit of not being susceptible to crazy outliers. You know, you take if there's some huge number at the end of the spectrum, or you know, my median hasn't changed because my median's worried about what's in the middle of the pack. Okay, that's great. Oftentimes people, when they're worried about outliers, scientists, when they're worried about outliers, will take median numbers instead. They'll go out of the way to get the median. Now, on that front, let's talk about the last one, which is mode. And does it have mode? We have the old mode. I doubt I'm going to have much mode here. What I'm going to do is I'm going to create a new data field. Data field 6. And I wonder if I can get, yes. Let's try that. Okay, that's not going to help us. We're going to do Poisson, lambda, just one, that's fine. No, just right here. Let's try that. Okay, here we go. So a Poisson distribution looks like this. Whoosh. See it again? Whoosh. Okay, so it's a curve with a long tail. And so the idea is it all bunches up, or Poisson or binary, they're similar, and they bunch up on the lower end, and a lot of things follow this pattern. They don't have a centrally located mean, or centrally located like a peak, like a bell curve or a normal distribution like this right here. Woo, woo. And the sound effects are essential. It's important to your statistical technique. Woo. Okay, right there. That's a normal distribution. That's what a lot of this average and median stuff is focused on, and what's normal. Well, what happens when you have a data field like this, where honestly there's a lot of zeros here and ones. So let's count if this is 0. There are 13 zeros. So let's go ahead and count it. No, let's make it 11 ones. That's everybody. Okay, so here are the zeros, the ones, the twos, and the threes. And theoretically, you know, this distribution could give us a 1 million, but that's just so far out on the whoosh tail, it's very unlikely. Instead, it bunches around. It bunches around here. It has to do with where you put the lambda when you with the Poisson distribution. But the point is, it bunches around 0 in this case. So we have 0. We have a lot of ones. So what is normal here? Honestly, the idea is mode is going to tell us. Well, let's do equals mode. We're going to use mode is going to tell us that if you take a random draw, if all these were put into a hat and you took a random draw, what is the most likely? Which number has the highest likelihood of you pulling out? Well, you're most likely going to pull out a 0. Of all the numbers, you're going to pull out a 0. This is similar to the dice. When you roll 2 dice, you are likely to get a 7. No, plus. you're not likely to get 7. Excuse me. But of the different numbers out there, of the rolls out there, the highest probability roll you could do. Let's do mode. No, not with an array. Old-timey mode. Highest probability bet you can make is 7 because there are more 7s in this. There's 1, 2, 3, 4, 5, 6. 6 different ways to roll a 7. Whereas the next highest is 1, 2, 3, 4, 5. 5 different ways to roll a 6 or an 8. 1, 2, 3, 4, 5. Okay, so if you want to make your highest probability play, you try to roll 7s. That's why it's the classic craps trick when they're doing it in the movies or whatever. Oh, I'll try and roll 7. But guess a 7. All right, so mode, median, and mean or average. Mean and average mean the same thing, right? Those 3 tell us what's normal in the data set, and they get us one number. Okay, I can handle one number. All right, well, probabilistically, the mode, the most often occurring, is this number right here. Or if we're talking about this data set right here, this right here. Great, mode tells us something. I got rid of the median here, but median, still have them in order, so. The median tells us something as well. And lastly, the mean tells us something as well. So we can just take one number or a handful of numbers and it will tell us something about this data set. We can't crunch these numbers in our brains, but we can crunch the highlighted ones, or it's the start of us crunching them. That's much easier. All right, so let's talk a little about standard deviation and go from there. We'll see where we're at from there. All right, so standard deviation is a measure of centrality. So say we have the typical way standard deviation is used is the idea of we have a normal distribution, and which means that we have some sort of distribution like this where there's a central mean, central most likely area or clumping of values right around here in the middle, and then there's a downward slope in both ways. And I'm very shorthanded expressing what a normal distribution. I'm being very brief with this idea. So the standard deviation tells us, well, okay, let's talk about how far in this particular data set is like a normal step. What's like normal. One standard deviation above or below the point of central tendency in a normal distribution should give us about 68%. This is the 68, 95, 90.9.7 rule. Should give us about 68% of the whole population or the whole sample, right? All right, you can see right here. 34.1% is in this little dark blue right here. 34.1 this percent. So together it's 68% right here, just within one each. The sigma is a standard deviation. So one little step down or above our mean or median, our mean or average, should give us almost or more than 2/3 of the population, assuming that it's distributed in a normal distribution. Okay, we go one step out more, so not just one, but also 2 steps out. So within 2 steps up, 2 sigma up, or 2 sigma down, sigma s, sigma standard deviation, that's what that comes from. We should have 95%. If you add all those numbers up, they equal about 95%. We should have 95% of the population within 2 standard deviations of the mean, assuming that the data is distributed normally. It has this tendency towards a normal distribution. That's what I mean. When I say it's distributed normally, I'm specifically meaning distributed with a central tendency towards a normal distribution. All right, and that leaves us 95%. That leaves us about 5% for the tails. 2.2% over here, 2.2% over there. That leaves about 4.4%, right? Okay, you got 3 standard deviations from what's in the middle. And you're talking about 99.7%. So 0.1 with some trailing numbers, 0.1 with some trailing numbers on this tail over here about what really high or really low. And so when we're talking, it's a measure of how extreme is this number. Let's go back to our data set real quick. Now, it helps us tell kind of the scale. Standard deviations help us scale the numbers. So each of these have about the same scale because, again, I randomly created each of these within a very standard. They all work between the same numbers. But let's go ahead and change that. Let's do rand between 0 and 100,000. 28,000 now. So let's go ahead and change data field 3 so that it's a much bigger number. Now we have the total sum of all the data values is 1.657 million, which means the average is 55,000. And now the standard deviation is 28,000, which says, okay, well, what is like a step away in terms of extremeness from what's normal? About 28,000. Whereas before it was about a tenth of that, because I increased the size of the plot, what's random between, by about a factor of magnitude. Okay, so yeah, if we're comparing these two right here, let's say we're looking at our count number 42 and count number 26, which is observation 13 and observation 5. They are, looks like, about $7,000, let's say dollars, $7,000 different. They have a $7,000 difference between them. If we had a scale like on data field 1 here, where 2600 is a step, a significant step, then we have there 7,000 divided by 2600. We have 2.7 standard deviations difference between these two. That means that they should be very far apart. This is a significant deviation between these two. But we don't have that scale. We have this scale. So when we look at these, we can say, you know what, that's actually not that big of a difference. But 28,000 is a standard deviation's worth of difference. So the 7,000 difference here isn't even one standard deviation's worth of difference between the two. It helps us say what's big and what's little given this scale. All right, so those are some real simple descriptive statistics that we can use that will help us. And the key here is, let's come back to it one more time with feeling, that we need to derive singular numbers from this vast data set so that we can actually comprehend them. Otherwise, we just can't compute this data right here. Your brain can't compute it. Perhaps if you familiarized yourself with this data and became good friends with it, you ate lots of local food and talked to all the local people and learned the language, you would eventually be able to be very familiar, and somebody presents you a new observation 31, and you be able to immediately say, well, this is in the normal range, this is abnormal. This, put down here the department number, right? So this department, wow, that department really exceeded expectations here. It did not do so well here. It did really great there. It's fine there and average here as well. You would be able to immediately say that if you familiarize yourself with all this, or because you don't have time to eat local food at this data set, you simply say, well, okay, it's number 31, data set 31, or observation 31 here has 10,000 here. The average is 5,700, and a standard deviation is 3,000. That's almost a standard deviation and a half away from the average, that assuming normal distribution, which we don't. This is actually not normal distribution, but if we were to assume that, then that's a good step away. That's a good performance. All right, so our numbers here help us. Let's move on to something a little more complex. So we have our data analysis, and let's go ahead and do some regression. Let's regress back to an earlier state. And so let's just go ahead and say we have a data field here. Well, it's the y we're trying to predict. It's the independent variable, and we expect that this data field here. No, that's still ran between. This data field here explains it, that something in here causes something in here, or at least there's a correlation. It's important that I put that caveat there. We are, strictly speaking, with this regression, we'll only be looking at an association. These two are associated. The arrow of causality is not yet known. That has to be figured out. That has to be carefully considered and thought through. And in the next lecture is what I want to think about when we talk about thinking like a scientist. Because now we're saying we don't just want to know what's normal. We've moved past that. We had our 4 statements about what's normal. We can pull out 4 different numbers that tell us what's normal. What's normal if we redistributed all the numbers? Like if it were perfectly smooth between all the numbers, what would be a normal number to get? If in terms of so for example, going back to average, assuming that it's a flat distribution, then what would be our normal draw? Which it literally is a flat distribution, so the average is a good number to use here. Median says, well, we don't quite trust that. We don't really want the edges of the sample to be affecting this. So what's normal in terms of what's in the middle of the pack for our data set, and this our field, our column in this case. And mode, what's normal if in terms of the most likely draw if we drew it randomly, most often occurring number here. And our standard deviation tells us what's like a normal step across the chart to give us kind of a delineation of how big of a scale this is. All right, this is starting to talk about regression and ANOVA, which is a special form of regression that's special enough that it just kind of you need to learn it separately. And a variety of forms of regression. These start telling us about associations and correlations. They're all trying to predict correlations. That's the key thing. Correlation means that when one thing moves up, the other thing moves up as well. We're looking at the association. How much do these things go up together? Correlation. Oh, well, you know what? When it's when it's sunny out, it tends not to be cloudy. So when I can see the sun, there tend to be fewer clouds in the sky. Could there be some clouds? Sure. Maybe it's a gap in the clouds. But in general, when I can feel the sun on my skin, there are no clouds. When I feel rain on my skin, there are clouds. Those are examples of things that go together. Or in sun, there's no clouds. So sun goes up. There's a negative correlation between me feeling sun. So let's say I feel sun, so it's a 1. The likelihood that I'm going to see clouds, or a lot of clouds, let's say some whatever counts as cloudy skies, goes down. So there's probably a negative correlation there. Let's say negative 0.5. So that's a correlation. Correlation between I feel rain on my skin and the likelihood I'm going to see clouds. Okay, well, if clouds is at 1, I feel rain, observation, that's a 1 instead of a 0. 1, correct, yes, I feel rain. I look around, I look for clouds. The likelihood that I'm going to see clouds when I look, probably 0.95. It's not very common that I feel rain and it's sunny out, but it happens. So that's a very close correlation. 95% is kind of the idea. 0.95. The correlation there is very, very close. Those two are very close together. So we tightly correlated. 0 would be there's no correlation. The idea of when it's sunny out, I get to drive a Porsche. No correlation there because it's sunny out plenty of times and I never get to drive a Porsche. So yeah, there's 0 correlation between the sunniness being 1 or 0, yes or no, or 1 or 0, and the likelihood of me driving a Porsche. No correlation. So that'd be a 0, an R, which is the typical representative of that for correlation, the R of 0. And here with regression, what we're going to be doing is we're going to say, okay, we expect there to be a linear, it's called linear regression, what we're going to be doing here, we expect there to be a linear relationship between these two fields. So in this case, we have column D right here, and we expect it to have an association, a relationship with column F right here. So when this goes up, in general, across this whole data set, we expect this to go up or down. We're gonna see where they tend to go. If F is really high, would we expect to see a really high or a low D? Or is there no relationship between the two? I mean, spoiler alert, there's no relationship because I literally randomly generate these numbers. But assuming they weren't randomly generated, there might be relationship between them. It might be driving one another, by causing one another. And so this is the beginning of us saying, okay, well, our data set is not just in a vacuum. They have relations. If you put together a relational table, the database, for example, one of the things that does is it helps you not only organize the data, but helps you perhaps find and think. Make sure I say this right. It primes you to think about relationships in this associated manner, this associations between different data fields. That's one of the advantages I find for that anyway. And so we're just gonna new worksheet plan. That's fine. So we're gonna have this output here. Okay, so we have here an R squared of 0.000104. So the R squared tells us. I'm just going to run through all of what this output tells you. So R squared here tells us that, a 1, an R squared of 1, would be that our model that we have perfectly explains the association between column F and column D. A 0, which is basically what this is rounds to 0. An R squared of 0 means that we have our numbers here explain nothing. They tell us nothing. about the association. There's basically no association, no explanatory power of this right here. All right, I'm not worried about much of the else. This is kind of a similar idea to standard deviation. It's not the same thing, but it's a similar idea in terms of giving us a scale of the variation. We have here a number of other regression level statistics. Some of the squares and the significance of the f value here. Another way of talking about well, does this tell us much? And we actually it doesn't tell us that much here, because we have the idea of an intercept of 5175.698. Okay, so we could draw a little Cartesian plane right here. Okay, so the intercept of where it intercepts the y-axis is at let's say this is 5,175. Great, the intercept is right. It's based on the y being column D, which we put into the analysis, and the x being column F. Column y intercepts at 0 when column F is at 0. The expectation is that column D would be at 5,175. That's what our model predicts based on the data. It's the best fitting model that we could do. What it's done is the computer's gone through and it's minimized the error. It's drawn a line and said, okay, well, how can I get this line to have the least amount of error from what is actually in the data set? And so here we are extracting singular values. The line, the definition of the line, the intercept and the slope, so that we can understand relationships within the data set. Look at that. We have taken relationships between two columns, total of 60 data fields, two columns with 30 observations each, and we have extracted two numbers from it. That follows my theme. We're trying to get it simpler so that we can take a few numbers that we can handle cognitively. Okay, now the second number, the x variable, which is the slope. The coefficient here, it says is 0.00976. So that looks like almost a slope of 0, which means a flat line right there. So let's go in there and let's draw our flat line. There it is. That is our expected relationship. So as the F column goes up and up and up, the Y column stays the same. About 0 relationship. The other thing we can talk about is p-values. So assuming a good number of things about there are a lot of assumptions built into regression here, a lot of ways in which you can make it more complex. And I don't know if we'll have much opportunity to talk about the different ways to do that. But here we've said basically making the assumptions that we have to about this association, this slope specifically in this case. What is the probability out of 1 being 100%? What is the probability that this is just that this number is actually 0? 95%, 96%. Yeah, it's almost certain that the slope is 0. This will round to 0 in the end. It's saying there's very low likelihood that there is a relationship here. The intercept's pretty spot on. Like that is a 0.0000562 probability that the intercept is equal to 0. So no, we know for sure that the intercept's not 0 at the very least. Now, I shouldn't have said it's spot on, but we know it's not 0. We know that we've got some number, and we may or may not have predicted it fairly. We've got a range here across which we're lower and upper 95 percentile confident that it rests between about 3,000 and about 7,500. All right, so the point, I'm getting kind of far afield here, but the idea here is we've extracted some values. Let's do multiple regression. Let's do that really quickly. It's very similar. We're gonna go very similar if we can. We have the x range again. Y range. Excuse me. We're gonna start again. We're gonna do y. Here is column D. We're gonna try all of column C. No, I'm trying to quote the Latin there. We have 3 different data fields. We're saying 3 different columns we think are going to predict. Let's get all of them and paste as. Now it'll just take whatever values now. It's not gonna Yeah, it'll work. It'll work. Doesn't matter that it's still wonky as values. All right. So let's go on here. We still have an R squared that's very, very, very low. That's low enough that you should say, I'm not sure that's explaining that much. We have here again we have an intercept of 4,520. We have an intercept about the same place before. And now what are each of these slopes telling us? In multiple regression, what these slopes are telling us is, hey, where's our beautiful Cartesian plane? Look at that. It's just art. Okay, so let's say this is the y-axis here at 4,520, and we're basically saying, honestly, spoiler alert, this is basically saying the same thing with some minor variation. I'm not sure why. It's probably random luck that some of these look like they have an association. But what we have here is we have slopes that are very close to zero, and the probability that each of them is zero is 26%, 80% here, 73% here, 65% here, and this is the slope. This is the slope between column F here. No, column E. Excuse me, because I did these. What did I do? Yeah, 4 different dependent variables. So I have 4 different columns. So column E here is the first one. Where was it going? Oh yeah, after we've factored out the relationship between these 3 and our y, our y, our column D, factoring out all of the other correlations that we expect, what is the correlation between this? And what we expect is it's 0.02. And so what we have here is we cannot use my art anymore, because this is a y and 1x. We don't have 1x. We have 4 x's. And so we'd have to make it 3-dimensional, and then 4-dimensional across time, and then 5-dimensional across Dr. Strange's or something like that. I don't know exactly what the 5th dimension would be. But yeah, that would be, we'd have to change our method here. And that's how you interpret this correlation. It says this is the correlation between our dependent variable, this column E, it's what our line has drawn anyway, what the expected correlation given the assumptions of regression, and our independent variable right here, D. Now then we go ahead and we have column F, column G, and then column H, and again they're all close to 0, and because I created them and they're all random, I know for sure that they are random. So there's no correlation between them, or shouldn't be anyway. If there is, it's just random luck. If we got bigger samples, it would be even clearer, and I think we would be in good shape there. All right, I think that's a good place for us to stop. And yeah, I've hit this hard enough that I think we're okay. As usual, I'm actually going to tease you, and I'm not stopping right then. Let me go through and list out. I wrote this down. I have a list of different parts of data analytics and how they map into the idea. We've gone over some of this, but let me just list it out here for you. So first of all, there's the question of descriptive statistics that I've covered, specifically mean, median, mode, standard deviation. All right, then we have regression and a variety of different forms of regression, including ANOVA, which stands for analysis of variance, and COVA, which stands for analysis of covariance, which the idea you have a covariance you're trying to factor out, and then you want to analyze the variance between these 2 other factors with the covariate factored out. And various forms of regression, some of which are useful for different types of data. If you're trying to predict a 1 or a 0, if you have a curvilinear space you're expecting, or splices, or a variety of different tools there. These are all helping us to learn the internal rules of the space, the associations, and if we reason it right, are likely cause and effect relationships within the data set. We have also the techniques of data mining and data scrubbing, which helps us discover and describe the internal rules more by helping us to avoid errors. So if we had that 1 million data point, maybe it's just somebody fat-fingered it and pushed the number too many times. Well, let's try and scrub the number. Let's try and mine, get good data so that we can then summarize it and have higher quality summaries of our that we can then talk about. So look when I did that, it changed the mean here, changed the standard deviation, and it threw off our numbers. So let's get clean data so that we can have a better description with descriptive statistics, and then with the regressions and ANOVA that we're going to use to describe the internal rules of our data set. Visualization helps us focus an audience's attention visually on some key descriptive statistic or internal rule, some sort of important relationship or number that we have pulled out of the data. We want the best visualizations. Really, the key again is to simplify down to 1, 2, or 3 ideas that you're getting across. You're trying to just be communicating something simplified about the data set. If you have a pie chart with 5 million different slices of pie, it communicates nothing, unless one of the pie pieces is enormous. And then what you're really communicating is, this piece of pie is enormous. You're saying one thing. You're not saying 5 million things. You're saying one thing. And so when you're choosing your axes, when you're choosing the fields on which you're creating your charts and your graphs, when you're deciding between line graphs and bar charts and so on and so forth, you have to keep this in mind. What am I trying to communicate? What am I saying? Is it appropriate to use a line chart if I'm not trying to show causation or relationship between the axes? No, usually it's not actually. So on and so forth. So, and if I'm using a bar chart, how is the x-axis organized? Is it ordered just randomly? That might not be the most useful. Is it organized rank ordered some way? Is there some reasoning to this? So these visualizations, these ways of presenting the data help us communicate to an audience so they cognitively can process our discoveries about the data. We have relational tables and databases that help us organize the database on its internal logic, which is not all cause and effect, but some of it is, and others of it are about subcategories and so on and so forth. So relational tables within databases help us understand the internal logic, help us organize the data based on its internal logic, so that then we can then reference the data with appropriately given its internal logic. And then we also need to start learning how to think algorithm. Another data analytics tool is thinking algorithmically, so that we can develop rules for data sets. If you start to think about algorithms, what that is to say, a set of steps that I can execute that will inevitably lead me to a particular answer, that will lead me to a predictable answer. Let's say inevitably probably doesn't deserve it there. Let me just restate that then. A set of steps that I can complete that will lead me to a predictable place, a predictable answer. Okay, as you start thinking about that, that'll help you set up processes for yourself so that you can, again, get these numbers that are cognitively palatable and digestible in an automated way. And that leads us then to programming, which requires proper syntax. Data analytics also includes the idea of programming, which allows us to automate our all of our simplifications that we've done, including the algorithmic ideas. So, hey, I know that when I get a data set, I want to get the average, I want to get the mean, I want to get the mode, I want to get standard deviation, I want to create regressions based on certain relationships I'm expecting between columns over here and columns over here. We can set all that up so that it does it automatically. We can program that in, and we have to learn the proper syntax for that. But again, that nestles within the idea of the data set itself is undigestible. We have to digest it first we have to pre-digest it with these tools. And now I'm done. That's all I had written. The idea of all this stuff that loads into data analytics and this semantic overload that we've done nowadays, it really comes down to the idea of our narrow perception. And that's it.